I wanted to give you a lesson kind of introducing the last part of the sound unit, which is about sound and how sound is created. So we said that sound is always created from some sort of a vibration. Remember in our last unit we talked about waves and vibrations. And in this unit I want to talk about kind of more specifics about what sorts of frequencies you can get from certain kinds of objects. So one of the examples we used was of a pendulum. We talked about how a pendulum has a natural frequency that when you set a pendulum in motion, it's going to swing back and forth with a certain amount of time based on some physical parameters. So depending on the length of the string we set is the key, but also depending on gravity and things like that. So a pendulum doesn't really make a sound, but this same idea carries forward with other types of objects and how they make noise. We can think of some musical instruments. Musical instruments pretty much boil down into one of three types of ways of making a sound. So you can, all the sounds that are made are what we call forced vibrations. So there's a natural frequency that the instrument wants to play at depending on certain conditions. So a guitar string is a good example where you pluck the guitar string and it wants to vibrate at a certain frequency. Now, the reason a guitar is louder than just a random string being plucked is that the vibration of the guitar string causes parts of the guitar itself to vibrate. The guitar is designed such that the bass of this and the body of the guitar vibrate in a couple different ways. So there's sort of air moving in and out of the little hole, and the body of the guitar is vibrating such that there are lots of different regions on it that can vibrate at different frequencies. Violin and cello and things like that are the same way, that it has this sort of weird hourglass shape because different parts of the guitar can vibrate at different frequencies. Okay, so if something experiences a vibration near it that is at or near its natural frequency, that thing starts to vibrate. And so when you play a violin and things like that, what you're doing is you're creating a force that causes a vibration at the natural frequency. So the natural frequency is, there are several different frequencies that can be played on any string. And as we learned in our string unit, or on our waves unit, when we set up the waves on a string lab, something I wanted everybody to see, that you could, with the same string under the same conditions, get several different frequencies. So there's more than one natural frequency. So I wanted to kind of explain that in this lesson. So we mentioned this in the waves unit, but I like to leave it in here. The Tacoma Narrows Bridge. We showed you that was a bridge in the 30s or 40s. It didn't last very long because wind would cause it to sway sort of at its natural frequency, and eventually it collapsed, I think, in the early 40s because the wind caused a natural frequency, sort of like a bow going across a violin string. That's sort of the effect that the wind had on it. Nowadays, they design bridges such that the wind doesn't have such a big impact, and they put things in the cables and things like that that absorb some of that energy of the wind so that it's not transferred directly to the swaying motion. So there's a link I'll put in the description of the assignment too. So if you've ever, maybe you've seen this at a dinner party or something like that, sometimes people will take their finger and in a wine glass and kind of rub it around the edge of a wine glass, and this causes sort of a musical note to be played from the wine glass. And this is akin to sort of any instrument that can play a certain tune. You can change the pitch of that by putting water in the glass because it's resonating over a different distance. So I wanted to explain how you can kind of do a calculation for that. There's a lot of factors that have to do with the sort of the speed of sound through that different material. But one big factor is the size. And we can always, if we know some of the other conditions, we can always calculate the frequency or frequencies that are possible depending on the size of the wave that's produced. Okay, so these are what we call harmonics. So if you remember the harmonics, we learned about this word when we were doing the waves on a string, where we could have our first harmonic was where it was like sort of pinched at the ends, but it could vibrate back and forth, just sort of one big wave. But we said that if we doubled the frequency, it sort of looked like an S, where it was sort of vibrating back and forth like this. This is what we called the second harmonic. We knew that since the wave has the same speed on this string as it does on this string, that the frequency here is going to be doubled, but the wavelength is exactly 1/2. So we can remember that velocity is frequency times wavelength. So here, this wavelength is half as much. However, the frequency is twice as much. Okay, so we refer to this lowest possible frequency and longest possible wave. You could think about it either way: longest wave, lowest frequency, as the fundamental frequency for that vibration. And we talked about this mostly with, we'll come back to that for just a second. We talked about this mostly with strings. So the string is always pinched on the end at what we call nodes, and then it vibrates kind of in the middle. And you can add a node in the middle to that, a part where the string doesn't really vibrate, and antinodes in between. And this is what we get as the second harmonic. The second harmonic frequency, which we call F2, is twice the fundamental frequency. The fundamental frequency we always write as F1. That's the lowest possible frequency, or the first harmonic that you can play. Okay, we talked about that with strings and so forth. And you can kind of work out some fractions, but I'm going to sort of shorten this up so that it makes a little bit more sense. So going in the most general sense, the harmonics are always even, or not even, they're always whole number multiples or integer multiples of the fundamental frequency. So this question asks, what is the third harmonic of a string if the fundamental frequency is 200 hertz? So the fundamental frequency, F1, is 200 hertz. Okay, so that means that the third harmonic, F3, has to be 3 times the fundamental frequency. So this is some pretty simple math here, but you know this would come out to 600 hertz. Okay, so the idea is the third frequency, or the third harmonic, is 3 times the fundamental, the lowest possible frequency. So, but this is for a string. Not all instruments are stringed instruments. So there's general rules for any kind of instrument. If the instrument, depending on if something is able to vibrate at the ends or not. So with the string, we know that the strings are sort of fixed at the ends. And so a string is always going to vibrate such that it's moving in the middle and fixed at the ends. But a trumpet wouldn't be like that. A trumpet makes noise, and a trumpet is sort of open at the end, right? So we can always make predictions about where nodes and antinodes. Remember, the antinodes are where there's movement, nodes is where it's pinched. We can make some rules about pipes and things like that as well, because we know where something's moving, there's going to be an antinode, and where something's not moving, there's going to be a node. So there's basically 3 different scenarios for all things that any sort of instrument that can create sound. So a string, which we just described, where there's nodes at the end, it's moving in the middle. A pipe would be something like a trumpet or a bugle, or there's, a lot of different pipe instruments. Or you could think of this as a pipe open at both ends, or sometimes we call these open pipes. The longest possible wave that you could fit in here would be such that it's open at the end and open at the other end. Okay, And I can't just draw a straight line down because that wouldn't be any wave. So I can only really get a half a wave in here if it's open at both ends. So there would be a node in the middle and antinodes at the ends, which is sort of the opposite of the string, okay? Because here there was an antinode in the middle and nodes at the ends. So it's sort of the opposite of that, okay? And you realize the second harmonic, okay, I gotta be open at the ends. Okay, but now I got to fit another portion of a wave in here. So I got to go kind of up and down. And then I got to go. That was kind of bad. But so now I have 2 nodes and 3 antinodes, 3 open areas and 2 closed areas here. And you realize this is really going to fit the same number of waves in it for each harmonic, because here I have really a half of a wave. Because if I was to kind of slice it here and move this portion to the other end, it would come right up here and it would look just like the guitar string. Okay, so you say, oh, that's going to follow the same rules. So strings and open pipes follow the same rules for how many harmonics you can fit there, and what the wavelengths will be on that harmonic. The one that's goofy is open closed pipes. So these kind of follow different rules because you have to have a node at one end and an antinode at the other. And so the portion of a wave that you fit in there is sort of goofy. The longest possible wave that you could fit in there, or the lowest frequency, would have a node at one end and an antinode at the other. And if you work it out, you realize that this is actually just 1/4 of one wave, because here I've got the wave would have to go all the way up and all the way down. So I'm going to move this picture here. So it's kind of cut off here, but you realize if this was a complete wave, it'd go one complete S. So I really only have quarter, quarter, quarter. I really only have 1/4 of the wave that's fitting inside this pipe. And this creates some sort of issues with what frequencies are even possible in an open-closed pipe. So an open-closed pipe, I brought an empty wine bottle here, and let's see if this works into a mic. So if you just kind of blow over an open-closed pipe, which a empty bottle really is an open at one end and closed at the other end, listen to this. You hear a really deep frequency there, okay? And you would expect that, like the string and the open pipe, that the next frequency that I hear would be twice as much. But that's not going to be the case, because you can't, if I have an antinode here at the end and a node at the other end, there's no possible combination where I could get something twice as long there, because that would have to either be closed at both ends or open at both ends. So the next possible frequency is going to be triple that, because I could fit 3/4 of a full wave in here. Okay, so what I'm going to do is I'm going to blow really hard over the wine bottle, and you'll hear that the frequency isn't going to be twice as high, it's going to actually be 3 times as high. So listen to this. So it's here kind of like a squeaking sound there. So that's 3 times the frequency of the low one. Okay, or it might even actually be 5 times as high. I'm not exactly sure. So it doesn't work quite the same way as with a string or an open pipe.